It is my pleasure to introduce a speaker today, Dr. Chris Carilli. Dr. Carilli is the chief scientist of the National Radio Astronomy Observatory since 2008. And until recently, he was also part-time John Baldwin Director of Research at Cavendish Astrophysics in Cambridge. He is also a recipient of the Max Planck and Humboldt Society's Research Prize. Dr. Carilli will be talking about the ASPECS survey. And without further ado, I now turn the control to Dr. Carilli.
Okay, yeah, well, wasn't actually sure how long this should be. It's going to be 25, 30 minutes long, I hope. And I was told not to really focus that much on the NGVLA, but on recent science. And so I thought I'd focus on results from the ASPECS survey. And it really started some 20 years ago with conversations between Fabian Walter and myself on trying to trace out what we call the dense gas history of the universe. Okay, you might call it the missing half of galaxy formation. The idea was really a simple one, and we've been pursuing this for 20 years now. It came with the first observations of molecular hydrogen in the distant universe. And oh, there we go. Good. So the idea is you take these deep fields at multiple wavelengths, in particular the Hubble deep field, the Hubble ultra deep field, beautiful pictures. And one of the great legacies of these deep fields is to trace out, I'll use my cursor here as a pointer, trace out the star formation rate density as a function of look back time, right back to the first stars in the universe. You know, and this is now a standard tool in cosmology. This rise in the star formation rate to the peak at about redshift 2, half the stars in the universe form, and then the fall to higher redshift. Really, one of the great legacies of Hubble Space Telescope. But one of the other major tools we use in galaxy formation is what are known as star formation laws. And I show here one incarnation of that, or I'm sure our chairman could give us a long talk on this. This is a relationship between, for instance, in this case, the far infrared luminosity of galaxies and the molecular CO1 to 0 luminosity. You can read off far infrared as star formation rate, a proxy for star formation rate, and the 1 to 0 luminosity is a proxy for molecular gas mass. It's very difficult to observe hydrogen, molecular hydrogen directly for good physical reasons. And galaxies form a nice locus on this, in this space, both on small scales and large scales. So the idea would be, going the wrong way, there should be a parallel evolution of the dense gas in galaxies as a function of redshift. This is where we started, as I said, some 20 years ago. In our review article 7 years ago, basically, we didn't know anything. Hence was the ASPECS survey born, the ALMA spectroscopic survey in the Hubble Deep Field. It's a very good team, very professional team, not too big, and everyone really participates fully, many different papers and different authors. First extragalactic large program with ALMA. We had a total of about 200 hours in the 90 and the 250 gigahertz bands of ALMA. And the idea was to do a blind volumetric survey to obtain a dense gas history of the universe, finding molecular gas unbiased by pre-selection on galaxies. So this was kind of the situation as of a few years ago in terms of what we know about the normal matter in galaxies. I show here the standard star formation history, the rise and fall, its star formation rate density. Then the stellar mass here, which is a steady rise with cosmic time. And indeed, if you integrate the star formation rate, you get a curve which roughly matches the stellar mass density independently observed when you include stellar mass loss. We also know about the neutral hydrogen in galaxies. That's from Lyman alpha absorption, damp Lyman alpha absorption at high redshift disk galaxies, and 21 centimeter emission at lower redshift. Question is, what's going on with the molecules? And that really was what was driving us, because this sort of is what is the direct relationship to the star formation. One slide on what is the ASPECS survey. I show here the ultra deep field over here on the left. We surveyed a 5 square arc minute region in the ultra deep field. So it was a mosaic with 17 pointings at 3 millimeters and 85 pointings at 1.2 millimeters. We did a full spectral scan of band 3 and band 6 of ALMA, 90 and 250 gigahertz. I show here a plot of observed frequency versus redshift. And you see the CO transitions moving through the observed bands, okay? So the game here is to, when you see a line, to try to match it up with a transition at a given redshift. There are other lines in our survey, carbon 2, carbon 1. I'm not going to talk about those today. 100 hours per band. We're going pretty deep in the line continuum. In fact, getting down to the knee in the mass function, molecular mass function, a few times 10 to the 9 solar masses, which turns out to be very important. And the deepest continuum image is made at 1.2 millimeters, below 9 microjansky's RMS, getting down to star formation rates of less than 10 solar masses per year. Total cosmic volume surveyed, given this 3 dimensions that we survey, is large, 42,000 cubic megaparsecs co-movement. So why do we do it now? Like, why didn't we do it 20 years ago? And the answer is twofold. One is ALMA. Again, sensitivity, literally in tens of minutes, half an hour, we're reaching down to the dominant galaxies out at high redshift in terms of their CO luminosity and the populations. High resolution, which allows us to identify sources, and wide bandwidth, which allows us to scan in frequency and get a large volumetric search. And really no less important is the UDF itself. There are thousands of well-characterized galaxies. It's really quite remarkable as we go through this, how important this has turned out to be. The deepest optical, X-ray, etc., as well as Muse spectroscopy of essentially the whole field, which allows us to do stacking in 3 dimensions, meaning redshift being distance. And that gives us well-characterized galaxy properties once we identify them, from the millimeter through the rest frame UV, get stellar masses, star formation rates, about as accurate as we're ever going to get them, as well as the Muse spectra. So it really is beautiful data. So I'm going to show you, in fact, since there's a limited amount of time, let me stop this. I'm going to show you the ASPECS survey. This is real data. This is the survey in 3 dimensions. It's volume rendered by the folks at Max Planck in Heidelberg. And what you'll see here is the optical image of the UDF. And eventually it will cut to the 3-dimensional volumetric cube of the line data. This is the real data now. This is the ASPECS survey. We're projecting the moment 0 image onto the optical. Now we deproject in redshift. It's pretty cool pictures. And then you spin it to see the three dimensions, redshift being distance. And there's our galaxies. It's kind of interesting physiologically that you can find fainter sources as it moves. Some of them may be noise, of course. So there's the ASPECS survey in full 3 dimensions. We'll wait for this to finish. It reprojects, and then you'll see a couple of galaxies as they line up with the optical field. We'll blow that up now, go into some region, and you'll see a little blinking CO. You get galaxies here and there. You can find the galaxies if you care to. All right, this is done. So let's just jump right into it. What are the properties of the CO selected galaxies? Again, the UDF is absolutely critical for this. I show here 4 typical galaxies from the survey. I really didn't pull these out in any specific way for certain properties. In terms of the numbers, we get 22 galaxies in either CO or the carbon 1 line at 492 gigahertz. 100% optical identifications, optical IR identifications. It is the UDF. Most of them detected in dust with ALMA. In terms of total lines detected, 32 CO lines, 7 carbon 1 lines. In other words, many of the galaxies have multiple transitions. I'll come back to that. Redshift distribution, well, not a large cosmic volume at low redshift. 14 galaxies in redshift 1.3 bin, and 7 galaxies out at the redshift 2, 3 or so bin. You can see some of them here. We have some edge-on disks. We've got some relatively face-on disks. We got some small galaxies. We got some confused or messy systems. In terms of line properties, got some very broad lines, 600 kilometers a second. Some nice double horn profiles, some relatively messy lines, and then actually some narrow lines, in this case, just 50 kilometers a second. In terms of the optical profiles and the X-ray, again, the UDF is critical for this. We find that the large majority, 3/4, are well described by exponential disks in stellar light, meaning, kind of spiral type galaxies. About a third, a quarter, are either small or confused or possibly interacting. 1/5 of the sample is AGN as determined through the X-rays. And again, the UDF data is really critical for determining physical properties. So one thing I want to say is that whenever you go see a talk, at the end, people always say, well, you know, we just got to go deeper. We got to go deeper. I'm going to say right now, we don't have to go deeper. This is about as deep as we need to go to do what we're doing. And I'll show that here. Oh, these slides ended up out of order. Let me show this one first. Oh no, wait, I'm sorry. Here's the millimeter continuum image. We get 34 dust continuum sources in the field. It is the deepest dust continuum image ever made at 9.5 microjanskis at 250 gigahertz. Most of them are detected in the optical. So one thing we can do, given that we have the Muse spectra, is we can do three-dimensional stacking, okay, because we have the lines. And I show here two different aspects of that, versions of that. One is stacking in the image domain. You take all the Muse galaxies, including the CO detections, and you add them all together, lining them up at zero velocity, and you get a nice detection. If you remove the detections, you effectively get what looks like noise. Similarly, Bada Özgil has done, that's an INAMI paper that I think that's just coming out. Bada Özgil has done a nice power spectral study, in this case a cross correlation between the ASPECS cube and the Muse galaxy distribution. And if you include all the sources, you get a finite correlation. If you remove the CO sources, you essentially get close to zero. We conclude that we're getting about 90% of the total CO emission in the field. So there's no dominant population of gas-rich galaxies that are kind of lurking underneath our detection threshold. You can do the same thing in the millimeter continuum. I show here the number counts, number versus flux density at 242 gigahertz. Black symbols are the ASPECS data. The colored symbols are other surveys where the data below the flux densities of ASPECS are actually lensing surveys, so small area. And there's been this debate as to whether there's a steep faint end slope or a shallow faint end slope. I think the ASPECS data is showing pretty clearly it's a shallow faint end slope. It's very flat. And indeed, if you integrate this up, you find that 90% of the, what you might call the extragalactic background light, is being detected in the observed sources. Another way of looking at this, and I haven't checked this actually, but I think Jorge told me that if we integrated for another 100 hours in the same field, we would only detect 3 more sources. So I think we've gone deep enough. So let's look at some of the properties of a CO selected sample. It's unique in that sense. It's not optically selected, it's not infrared selected, it's not radio selected, it's a CO selected sample. I show here some of the properties. Here's metallicity on the left-hand side versus stellar mass. Okay, the gray symbols are the rest of the Muse main sequence or disk-like galaxy sample. The ASPECS sources, this is the redshift 1.3 sample, really fall at the high mass end and the high metallicity end, really solar or supersolar metallicity and high masses in terms of stellar mass. Now I show here on the right the standard main sequence plot, and I'll explain this in a little bit of detail. This is star formation rate versus stellar mass, okay? And it is now well quantified, I think, that star-forming disk galaxies like the Milky Way form a locus in this plane. That locus changes with redshift. This is the locus at redshift 1.4. Again, the gray symbols being the rest of the Muse galaxies, the blue symbols here being the ASPECS galaxies. And you see that the ASPECS galaxies sort of scatter around the main sequence. Important point here is if you had a starburst galaxy like ARC-220, the star formation rate for given stellar mass or gas mass would be 10 times larger, okay? So these galaxies, the ones that we're seeing, are not starburst galaxies. They really are falling on the main sequence. They're the high mass end of the main sequence. But in terms of this main sequence distribution, that's kind of where we're at. So what we're building up to is to try to determine the dense gas history of the universe. And you need to know a couple of things. If we're going to use CO 1 to 0 emission as the proxy with some conversion factor, we're going to have to be able to extrapolate high order transitions, which we measure, to the CO1 to 0 luminosity based on an excitation. And I show how we've done that here. Nice work by Leindert Bogart and Dominic Riechers in the Cold-Z survey with the VLA. Important point here is this is the distribution of redshift of the ASPECS survey on the right, upper right here. And these are the bands that we cover. And all of our galaxies have multiple lines covered, not detected, but at least covered spectrally. And in particular, the redshift 2.5 sample, we see in the VLA CO1 to 0 directly through the Cold-Z survey. That's a really important anchor point in all of this. On the left here, you see an example of the different spectra for one source. This is 2.5 redshift source, CO3 to 2, different CO high order lines at higher frequency, as well as some other lines. Beautiful data, by the way. And it will go public in the next month or so. So in terms of the excitation, here's the standard CO SED, CO luminosity normalized by the 2 to 1 line here on the left, redshift 1 sample, and by the 1 to 0 line in the redshift 2.5 sample. We're finding that our sources are relatively modest excitation. Milky Way rolls over in this plot. Starbursts have much higher excitation, meaning higher density, higher temperature gas. But star-forming disk galaxies usually follow this lower excitation curve. At higher redshift, we get somewhat higher excitation, the green curve. That might be expected since we're selecting on a higher order transition. But generally speaking, moderate excitation for these sources. And the other thing we have to consider is the star formation law. This is the empirical star formation law for our galaxies. This is CO luminosity on the left. Unfortunately, Leindert inverted the axes, and 850 micron or far infrared luminosity along the x-axis. Gray points are low and high redshift galaxies drawn from various samples, and the colored points are the ASPECS galaxies, which generally fall on this, what you might call the star formation law plot. So the goal is to convert these to physical quantities. Star formation rate, well, we have about the best SEDs sampled that you can get. So besides for the, the IMF assumptions, et cetera, we're doing as well as we can. The CO conversion factor, that's a different issue. Standard relationship is a linear relationship between gas mass and CO luminosity. We adopt the normal galaxy for what you might call spiral galaxies or main sequence galaxies. And you can ask Alberto about this if you like. Why do we adopt that value? First of all, well, we see morphologically they're mostly disks. Secondly, they lie along the main sequence for star-forming disks. Third, they're solar or higher metallicity. And fourth, they have moderate excitation. Now, this could be wrong, okay? But this is what we're running with. This seems to be what the data is pointing us at, and we're gonna run with it and see where we get. So here are the gas mass relationships, star formation rate versus molecular gas mass on the left. And you'll see the ASPECS points scattering in here along a line that's defined by a gas depletion time scale, which is the ratio of the gas mass to the star formation rate of about 1 billion years. And we'll see later, this is pretty much standard and invariant for star-forming galaxies across the universe, really, amazingly. The blue cloud here is another sample of optically selected high redshift CO mini galaxies. Again, starbursts would be 10 times higher than this in terms of their star formation rate. So following a fairly typical gas depletion time. And then the plot on the right, maybe the most interesting plot in the whole talk. And more importantly, I think it's correct, which is the ratio of the molecular gas mass to the stellar mass versus redshift. The clouds here are low and high redshift samples chosen in other ways, blue and green, and then the colored symbols being the ASPECS galaxies. And this is, I think, a fairly now well codified result in this increase in the gas mass fraction of star-forming galaxies with redshifts. Really, it's significant. It's less than 10% at redshift 0, and then greater than unity at high redshift. So it shows a fundamental change in galaxy properties with redshift from stellar dominated to gas mass dominated. Galaxy formation is just a messy problem, right? And you look for basic truths in here. And this is an empirical statement, which again, I think is correct. Now, I must say it's a little disappointing. We didn't see any gas-only galaxies. All the galaxies have stellar counterparts, but some of them actually have a lot more gas mass, molecular gas mass, than stellar mass. So what you can do is you can add up all the galaxies in these samples at the different redshifts, and you get the dense gas history of the universe. And I show that here, density of H2 co-moving versus redshift. The red boxes are the ASPECS sample. The colored boxes are high redshift galaxies selected in other ways, but observed in CO. The symbols here, the circles, are gas masses derived using dust continuum luminosity and a different conversion factor. Completely different talk, and more power to them. Fortunately, they all kind of line up fairly nicely. Most of the indicators are showing this rise of the gas mass redshift and then a slow decline as a cosmic average, anchored, of course, at low redshift by large surveys of nearby galaxies. So this is where we started, okay, and this is where we're at. And you can see this parallel rise and fall in the dense gas history of the universe, which one could argue is driving the star-forming history of the universe. Now, I could end here, but I won't, because now that we have all the numbers in front of us, we can start playing some games, do some numerology, and see where that takes us. So if you would indulge me for a minute. You also know that everything I've said so far is strictly phenomenological. I haven't actually said anything about galaxy formation, and I probably won't right up to the end. But you know, one thing we think is going on in galaxy formation is galaxies form along the intersection of filaments in the intergalactic medium. These are from hydrodynamic simulations. The baryons and the dark matter flow along filaments. Where they intersect, you get the formations of galaxies. You get a virial radius, a virial shock, defining the sort of circumgalactic medium, the gravitational potential of the halo itself, heats the gas, but the densest gas can flow in along dense filaments, eventually feeding the inner disk and star formation. So you have this picture of gas. This is a cartoon over here in the left, flowing in, hot gas flowing in from the intergalactic medium into a circumgalactic medium, the dense filaments flowing onto a disk of H1, conversion to H2, and eventually stars. Everything I've talked about has been these inner disks. But in sort of implicit in this discussion is this net flow, this net accretion from the intergalactic medium. But we'll see why that is in a minute. So let's take a step backwards and think about the cosmic baryon census. This is a really fun plot. The more I look at it, the more fun it is. This is cosmic density, mass density, co-moving versus redshift. Obviously, dark matter dominates and is invariant with redshift. The baryon density is high, and that's derived, and that's also invariant with redshift, and that's derived by observations of, for instance, the redshift of recombination, sound speed at recombination. The black line here is the sum of all the stuff that I was just talking about: stars, atomic hydrogen, and molecular hydrogen. You see, at low redshift, we have a very nice census. Mike Shull and Tumlinson, it's a typo. They show that most of the gas in the universe, baryons in the universe, is the hot intergalactic medium, 82%. Some 4% are in clusters, 5% is in the circumgalactic medium, still ionized, and then some 9% are in galaxies. Okay, and that's mostly stars at low redshift. The red line here is the stars. The blue line, again, is the molecular gas. The green is the H1. And the yellow line is the sum of the H1 and the molecular gas. So mostly stars in terms of the baryons at low redshift. As you move out in redshift, what happens? Well, the amount of matter in the universe in galaxies itself goes down by more than a factor of 2 by redshift 4. H1, again, is relatively flat, a slow decline with time. H2 has the rise and fall. And you get this nice transition between stellar-dominated versus gas-dominated galaxies at about a redshift 1.5. So what can we do with this? Well, the first thing we can do is quantify, well, the thing we want to do is quantify the accretion onto galaxies. And there's a nice paper that Fabian has just, I think it's just about accepted in the APJ. It'll be coming out soon. I'll show here on the left the gas depletion time scale versus redshift. This is the ratio, again, of the cosmic averaged molecular gas density versus the cosmic average star formation rate. That's the blue curve here. You can see it's relatively constant in time, from about 5 times 10 to the 8 up to about 10 to the 9 years. The gray line here is the age of the universe. The fact that these differ by so much tells you that you need gas accretion, right? You have to replenish the gas in order to maintain star formation, okay, at all redshifts. But we can quantify that better because we now have all the measurements, right? I show these here again on the left. So Fabian has gone through and developed a very simple system of equations which are based on the star formation history of the universe, the red curve here, okay? And the measured derivatives of the green and the blue curves, which are also measured. And that, it turns out, a linear sum of those quantities gives you the accretion rates, ionized hydrogen to atomic and atomic hydrogen to molecular hydrogen. And that's the yellow curve here, and then the black curve as well. So the dominant term is the star formation rate, okay? And any differences in here have to do with these derivatives in the other quantities, which have to do with either the depletion or the buildup of gas in galaxies. So at high redshift, let's look what's going on. The accretion rates are actually higher than the star formation rate, while the derivative in the H1 is relatively flat, but the molecule, so it's a pass-through phase. The gas is just moving through the H1 and actually building up positive derivative in the in the molecular gas. Intermediate redshift, these curves start crossing. The derivative of the molecular gas is roughly 0. It's turning over, so it's sort of a pass-through phase, but the hydrogen is depleting, and that's what's maintaining the star formation rate. And then as you drive down to the lowest redshifts, everything is declining with time, the star formation rate being driven by this general decline of the accretion rates and the depletion of molecular hydrogen. So as a final speculation, I think I'm doing okay for time. This is kind of my last slide. What causes the fall in the accretion rate with time? This is sort of a speculation. At high redshift, people talk about feedback, AGN star formation, heating the gas, keeping it from falling in. But as you get down to redshift 0, these rates, AGN rate, star formation rate, are going to 0. So that has to become less relevant by definition. Now we certainly know, and over here I show a plot of the buildup of dark matter halos with redshift, and these, due to the expansion of the universe, the accelerated expansion of the universe, this is declining with redshift, and that obviously the baryons are going to follow that, and the accretion rates go down. But let me speculate that perhaps only the densest gas in the intergalactic medium was able to cool and flow into the disks along these cold streams. Okay, that's just a speculation. So then you could say, well, perhaps only the densest gas that was predestined to fall in has already fallen in, and we've sort of done everything that we're going to do as a function of time. So I show here on the lower left a plot of the cosmic mass, again, this cosmic mass density, but now versus, lost my cursor, versus cosmic time. And the idea is that the accretion rates slowly drop towards 0. The stellar mass in the universe saturates, and one could conclude that what was destined to happen in the universe has already happened. And then as the future moves on, the stars will slowly cool and turn into degenerate rocks, and the sun will set in the west. So on that cheery note, what will the NGVLA do? I had to put in one slide on the NGVLA. You know, and obviously the 10 times the sensitivity and 2.5 times the bandwidth, you really increase by 100-fold the gas detection rates per hour, let's say, in CO. And in fact, you will be making, in modest amounts of integration time, molecular gas mass images that have galaxy densities that rival the deepest optical fields today. And you will be able to determine a very accurate dense gas history of the universe, which would then go on alongside the Hubble space or the JWST determinations of the star formation rate. So that's kind of where we're at. I'll leave out my summary slide and perhaps just leave it at that, given that I've been going for 30 minutes. Thank you.
Thank you, Chris. So we have a number of questions from the audience, and I'm going to start by one that ended up in the answer.
Should I stop sharing my screen?
Whatever you need to do to explain the question. So there is a question here about how the metallicity influences the CO results for the aspect sample. So would you worry about the metallicity effects in the results?
Well, as I said, they're generally sort of solar metallicity. And supersolar, which would then drive you, I guess, towards a lower alpha. But other than that, I'm not sure it would. If you lower alpha, then the gas masses go down, and that would obviously, alpha will scale everything up and down, and that remains, So the answer to the question is it folds in through the alpha parameter, the conversion factor, and if you drop that, then the gas masses would all go down, and then if you stare at this plot here. One could ask the question, what would that do? And I'd have to scratch my head on that.
Okay, good. So another question is about CO. You said that the CO and 250 gigahertz emission of the selected aspect sources accounts for 90% of the total emission. So what fraction of the total SFR and stellar masses at those redshifts do the aspect sources account for?
Oh, the star formation rate, I guess. I would assume that since we are, in terms of the far infrared, one would say that that it would then be, of course, again, 90%, because there's kind of this, yeah, you would have to, I haven't done that calculation. You would have to correct for those galaxies that don't have a lot of dust, but still have star formation. But generally speaking, there's not that many of those out there. So I would think we're still getting the majority of the star formation in the millimeter detected sources. But I will have to check that. And they asked about the CO.
Well, fundamentally.
Remember, the CO sample and the millimeter sample are different. There's some overlap. There's a 34% overlap. So the CO galaxies don't account for all the star formation, more so than the dust.
Okay, so another question. We have another question here about the fact that the UDF is a tiny patch of the sky that may not be representative. Worse yet, the UDF was chosen because of the lack of bright sources in the existing multivalent data.
That's right.
So how sure are you about that?
So in terms of, let me just answer the question in one way first, which was what Jorge Gonzalez, I was talking to him yesterday, or maybe the day before, said that when we say that we're getting 90% of the source counts, let's say in the millimeter, we have to include the phrase in the UDF. Other fields could be different, okay? Now, a lot of people have gone through trying to determine the large scale structure in which the UDF is embedded. No question about that. And I think the conclusion is that as far as we know, it's an average field, but certainly, yeah, 5 square arc minutes is, you have a cosmic variance issue. Overall, our cosmic volume is fairly large because of the redshift coverage. But yeah, that's a significant issue is cosmic variance. And again, I could say that if we go here, that would be the goal of doing this with the NGVLA, is not really to go much deeper, but to cover a much larger area. Instead of doing 5 square arc minutes, we do 50 or 500 for that matter. So I think that is, we have to leave some questions open for our future telescope.
Good. So there is a follow-up to the question of the fraction of SFR. So the question here is, or the person who asked the question was wondering about whether there is H2 in the lower mass sources that aspect doesn't detect, or whether the H2 is not emitting in CO. So do you have a guess at that?
you'll have to, you're saying H2 CO dark galaxies?
I think that's
is that essentially the question?
I think that is essentially the question.
Yeah, I don't think we can answer, we can't answer that question with our data. We certainly know that our galaxies that we see are high metallicity, but maybe that's by definition, we detect CO bright galaxies. I don't think we can actually answer that particular question with a CO selected sample. I'm not sure you can answer that with a dust selected sample either. Not exactly sure how you address that. Now, do I know that much about CO dark H2? And does that dominate the mass in nearby galaxies? And I will refer that question to our chairman.
You are the, I decline that.
Ah, come on, you just wrote a review on it. Well, a few years ago. Is there a lot of CO dark H2?
Well, I mean, it depends on the metallicity, among other things, no? So.
Yeah, I'm just talking about cosmic average. All right, we'll have to look that up.
Okay, so we have a few more questions here. Let's try to get through them all. So one question is about the number of these galaxies. Oops, things keep changing here, sorry. The number of these galaxies in the UDF. So do you think the number, given that the number of these galaxies in the UDF, do you think the number of galaxies detected in ASPECS is about right? I'm thinking about, or the person here says, thinking about what you may have expected a priori. And if there are non-detections of these galaxies that look like they would have sufficient molecular gas to show up.
Yeah, we looked into that, both in terms of the dust and the CO through the stacking analysis. And as I said, we don't, Inami, I'd have to go back and look at her paper, but she doesn't find a lot of CO in the fainter optical galaxies, that's for sure. And similarly, Richard Bowen's derivation of the star formation history of the universe based on the ASPECS data and UDF data does suggest that at very high redshifts, dust obscuration becomes becomes less of a factor in determining the cosmic star formation rate density. So I would say, based on the fact that we have the Muse spectra, I would suggest that we are actually not, as I said, missing a whole lot of faint CO galaxies. It's based mostly on the stacking and on the cross correlation in the power spectrum, which is sort of the same calculation, but different.
Okay. So you were making the argument that you didn't need to go deeper. But the basic tools like binning in redshift or smoothing a bit in right ascension or declination didn't result in more detections?
If we went at lower spatial resolution?
I guess lower velocity or spatial resolution.
Yeah, lower physical resolution. We went through that exercise in pretty gory detail. I think we have the answer is that no. I mean, the intrinsic resolution of the ASPECS survey was of order an arc second, right? And we explored search algorithms at least up to galaxies that were 2 or 3 arc seconds in size. I don't think we're missing a whole lot in that sense of over-resolving the galaxies. I think that's a fair statement or a safe statement. Of course, you never know.
So another person is asking, did you take into account the influence of the CMB on the CO line?
Yeah, that's dealt with in Roberto De Carilli's paper in quite some detail. I'm not going to go into it unless I can pull up the paper and read it to you. But he has a whole section on that, because that will suppress the low order transitions. We're not quite at high enough redshift here. We're at redshift 1.3 to redshift 2.5 or 3, and dealing with transitions of somewhat higher order, like 3 to 2 or 2 to 1 at the most, at the least. So I think it's not going to be a huge correction. But again, I referenced Roberto's paper. I should show that instead of showing all this. These are all the ASPECS papers that we published or are in press for those interested in following up on the talk.
So another question is about the fact that if you stack on the UV rest frame emission, which is what you're doing for deriving some of the conclusions. I mean, if you were to repeat that experiment in the local universe and construct a sample of local galaxies selected by UV emission, you may, reach broad statements that are, are not necessarily what we understand now. So are you worried about the effect of the sample selection?
Well, I mean, that's the reason why we did ASPECS, is that we didn't actually select the CO galaxies on anything, right? We just looked at a blank field and looked for CO. The only time the optical selection came in was when we did the cross correlation or the stacking. And in that case, we needed redshifts for the galaxies. So obviously they had to be relatively brightish galaxies to give a decent line redshift to do the three-dimensional stacking. But in terms of the CO selected sample itself, well, that was the whole point of the survey, was to just not select on anything but CO.
Okay, so we should probably close now. But thank you very much, Chris, for the talk. And
Sure.
Thank you, all the audience, for attending and asking those wonderful questions.
All right, well, that's all I had. Thanks for your time.